Hello, welcome to my talk. My name is Federico Larroca. I'm going to talk about Geotempest, which is how to spy video interfaces through electromagnetic emanations by using a GNU radio. So what I mean by Tempest is to spy on a monitor. So I'm going to show a demo right off. We are going to try to spy on the monitor on the behind that laptop, which is connected to this BGA interface, which is shown here. Geotempest is running on the laptop, and once the system converges, we are going to see that it is possible to see, for instance, there's the text on the right, there's the icons on the left, there's the writer icons here, and it's being spied on. This monitor on the back on the laptop is being spied on by this very simple dipole antenna here. So the message here is that it is possible. This is not a laboratory scenario. It's a very simple scenario. So the rest of the talk is how can this be achieved. So the problem of Tempest goes way back. It goes to World War II. However, these problems and the technology that was used to spy on the electromagnetic signals emanating from equipment was remained restricted to military and government for several years. So the term Tempest is actually for all to spy, generally speaking, to spy on electromagnetic emanations. We're going to focus here on electromagnetic emanations emanating from video display or video cables or connectors. And the first public demonstration of these techniques was around 40 years later. It was 1985 when Wim van Eck published his paper on eavesdropping CRT's monitors. So this is why Eck Phreaking is sometimes used as a term to refer to Tempest applied to video. And most notably on the great book by Neil Stephenson, which is called Cryptonomicon. So almost 20 years later, in 2003, Marcus Kuhn published a technical report on how to spy modern video displays. So in this case, we're talking about BGA and HDMI or DVI on not in CRT monitor, but on modern displays. So in 10 years later, in 2014, Martin Marinov, a master student of Marcus Kuhn, published Tempest SDR, which is an implementation on SDR of the Tempest or the Eck Phreaking technique. So what's Tempest SDR? It consists of three big blocks. It's one a Java-based user interface. There are several modules that do the DSP. These are written in C, and there are several plugins that interface with the SDR hardware. So about myself, in 2017, 2018, we worked along Pablo Menoni on his thesis, and during his thesis, we used Tempest SDR. And during 2020, in the beginning of the pandemic and during the lockdown here in Uruguay, I developed GRTempest. So GRTempest is basically an implementation of Tempest in GNU Radio. It may be seen as a re-implementation of Tempest SDR on GNU Radio. So why would I do this? So my objective was to take advantage of GNU Radio to address the problem. So first of all, it should be easier to code. I had to focus mostly on the general work function, which is the philosophy on GNU Radio, is to focus mostly on the general work function. then I would get all of the advantages of GNU Radio, support of GNU Radio, all SDR hardware support GNU Radio. So I would get that if I implemented Tempest on GNU Radio, I would get that by free. And furthermore, there are several blocks and functionalities that are already implemented on GNU Radio, such as filters, resamplers, the video display, and along, etc. So my idea or my objective was to simplify experimentation and extending Tempest by implementing in GNU Radio. So, having motivated and introduced the problem, let's talk about how to spy on monitors by using GNU Radio. So, I'm going to talk mostly about BGA. The digital case will be a relatively simple consequence of BGA. So, let's focus on BGA first. In order to understand BGA, the signal is simply, this is the monitor. Of the whole monitor, there is a part that it's what you actually see. There's what's called blanking, which is zeros on the signals around the image you're seeing on the monitor. And it is sent on the cable. The voltage is proportional to the component or the color of the corresponding pixel, or the intensity of the color of the corresponding pixels, and they're sent one next to the other on a horizontal. These arrows show how these are sent over the cable. So what you will get, this is a simple illustration. You'll get the pixel intensity corresponding to each of the pixels, a blanking, and again the pixel intensity or the color intensity of the corresponding pixel, one after the other. So actually, this is, if one remembers your communication curves, this is actually a PAM, pulse amplitude modulated signal with a rectangular pulse, or approximately rectangular. You may also see it as the output of a zero-order Hall digital to analog converter. So the math here of on its spectrum, that is what we're going to try to spy, is not very difficult, but we're going to go through it. So assume xi is the pixel sequence, which is indexed by I. TP is the pixel duration, and PT is a rectangular function, which is the pulse function. So thus the signal on the cable, it looks like this. It's xt. It's simply the summation of the pixel intensities times the pulse. So this is one of the colors. No, assume it's a red one, just as an example. So let's see what's its Fourier transform. This is very basic Fourier transform property, and we're going to take then the Fourier transform of the pulse. It's going to go outside the summation now, and we get that the Fourier transform of the signal on the cable in red here is the Fourier transform of the pulse times a Fourier series where the pixel intensities come into play. This is actually to be more graphical. I'm going to show here the spectrum. Here in black, it's the Fourier transform of the rectangular pulse, which looks like a sink at the pixel rate. Then in blue, we get this Fourier series, which is periodical, and it's actually the monitor to receive the image will actually focus on the baseband component of this blue signal, which is multiplied by the black Fourier transform of the pulse, which I'm not showing here because what we are actually interested here is on this part, on the harmonics every pixel rate. So in red, I'm showing the multiplication of the blue signal times the black one. And that's the one we're going to try to capture with our SDR. So this red part is the one we're going to receive with a GRTempest. So we point our antenna to a BGA connector, the modulate at 1 over TP, that's the pixel rate, and consider its magnitude so as to avoid frequency synchronization issues. This will be discussed with more detail later. What do I get? Well, I get this, which is not very useful. We can see there's something there, but we don't see any image. So the most difficult part is time synchronization. That's the problem. We have to generate signals and we have to feed them to our video display so that we get the vertical resolution number of lines per frame. So once we do that, we get images like this, where I'm going to play with the sampling correction parameter, so as to show you that when the sampling correction is not correct, you get skewed and moving images, and when you find the right sampling rate, you get a steady image, and that's what we try to do. We try to resample the image so that you will get a steady and a framed, to say it in a way, image. So let's see how this is achieved. This is the simplest flow graph on our examples folder, and we're going to go through it very quickly. First, you may use either a USRP or a previously recorded signal. This is very CPU intensive processing, and so offline operation is more than foreseeable. So the other thing, or the important aspect here, is that the total resolution of, that is the horizontal and vertical resolution, and it should include blanking too, that's important, and the refresh rate have to be manually set. So that's one of our future work features, but you have to manually set it. But once you have chosen your horizontal and vertical and refresh rate, that results in a certain pixel rate, which is simply the number of pixels per second, and that means that your USRP should point at pixel rate times certain harmonic. Sometimes the first harmonic works best, sometimes the second. That depends. You have to play a little bit. That depends on the video card. So this third block here, the fine sampling synchronization block, is the one that takes care of resampling the signal so that you will get the number of lines you want, so that it may be seen or may be displayed by the video SDL sync right here. So what we input here is, the parameters here are the interpolated horizontal size, that is how many samples roughly correspond to a line. But what actually has to be, you have to choose precisely, is the number of lines you have. If you miss the number of lines, you will get, again, as I showed before, a skewed image that moves. If you don't precisely input the horizontal resolution, you'll get a more or less a line with more or less pixels, but the image will be steady. Because how does this fine sampling synchronization work? It looks for correlation on the signal on a lag that is around a frame's worth of samples. This is obtained from the two parameters you input here. It looks for peaks on this autocorrelation, and it will interpolate the signal so as to generate horizontal times vertical samples between each of the peaks. So the important thing here is to, once you have these H times B samples between peaks, and these peaks should correspond to frames. So once the video SDL sync shows the resulting image, the important thing is that each lines actually correspond to a line. So it's very important to choose the vertical pixel parameter correctly. Now the rest of the blocks are somewhat basic. This delay here is to place your image in the frame. We are working on a block that automatically do that. Then we ask for the magnitude. This will be discussed later in the presentation. We then normalize our flow so as to prepare it for the video SDL sync, which uses shorts. So this has to be offset and normalized. Then we use this little multiplication by -1 and 1. There's a typo here. It should be -1, but in any case, it's simply to negate the signal and to invert colors. This sometimes is better to see it that way. And finally, this other path here, this is very important too. Again, since you have to yourself see what's the best or what's the resolution that actually works, especially the vertical one, it's typical that you explore and change these two parameters. And if you are choosing and exploring, you should use this other path here, because the video SDL sync does not adapt or change its parameter on runtime. So we've prepared this little block here that takes care of that. And so in the case you're searching for the actual resolution, you should use the upper path here. So some practicalities. First of all, the image has, as I mentioned before, a null on the center frequency here. This is the red arrow here shows it. So this is actually, you can see it as a high pass filter or as a sort of a horizontal border detector. You may see it very clearly here. There is no fill on the image because it will detect jumps on the signal. So if the signal is steady, there will be no signal to spy on. So images have no fill. And another, it's very visible here. There was a horizontal line here, which is not present on the image being spied on. The other thing is that you need somewhat large bandwidths, at least 20 megasamples per second. Sample losses at this point complicates visualization because the image will start jumping. I'm going to show it right now. We're working on automatically centering the image, and interferences, which will be visible here, further complicates visualization. So I'm showing here in the upper part 20 megasamples per second, and on the lower part 50 megasamples per second. And you can see that naturally, the larger the sampling rate, the better the image you will get. And you can see this movement there correspond to samples that were lost. So another practicality, you want to show or want to do a demo of this, and you're not getting any video at all. Or you don't have a high gain antenna. I showed a video using a simple dipole. If I'd have a nice directive antenna, I would get nice images. But what can we do if we don't have a high gain antenna and I have a simple dipole, as I mentioned before? So we can use a chip connector as the one I'm showing there. Chip connectors act as a sort of high gain emitter. So at the beginning of the video, you could see that it's here. You could see that there was no image at all. And then when I connected the chip connector, there was very clearly, it is very clear the difference between one and the other. So that's an interesting thing to take into account. And finally, what about HDMI? So HDMI or DVI, so digital in general, we may do exactly the same. We may use exactly the same flow graph, and you will get an image. The most important, so here you can see the most important difference is on the image itself, where now the image has fill. Why is that? Because In HDMI or DVI, they both use, so each color is encoded, has a different pin. That's the same as VGA. But now, instead of encoding each level or pixel intensity by a single number, they are encoded by 8 bits, which are then encoded into 10 bits by the so-called transition minimized differential signaling. This uses a differential encoding, and this means that even if the pixel is the same along a line, the encoded bits will be different, or typically different. And this means that even if the line is the same, it will generate signals outside the null. That was the one that resulted in a border detector. So it is very different, one signal from the other. VGA is very different to HDMI. In terms of the image itself, but the flow graph, it's the same flow graph works as is. The difference is that now we have to point our USRP, the center frequency should be 10 times the pixel rate. So for the future, there are several things we want to do. First of all, we want to automatically infer the resolution of the monitor. I mentioned before, we want to recenter the image automatically too. The other thing is, do we really need such high sample rate? Well, yes, if you want to see details, but we don't need 60 Hertz refresh rate. We don't want 60 images per second. So we're working on a method to drop frames instead of lowering the sample rate, because you have to have like a very powerful PC to process at such sampling rate. And finally, this is very early work, but let me show you here why should we consider the magnitude of the signal, which I mentioned more than once. So if we consider the magnitude, we get an image like this. This is a zoom in into one of the videos I've shown before. We see, for instance, here you may see that it says YouTube, but it's not very clear. Let's take only the real part, and we get a clearer image. It reveals more details, but the problem here is the frequency error, which is visible due to these sort of black and white lines that appear here. But certain things are clearer to see. So here it's much clearer. It says Tempest SDR. Now that you know it, you probably read it. But here it says Tempest SDR remotely eavesdropping. It's easier to see. The problem is frequency error, and we may even try to equalize the signal to reveal further details. And here I'm equalizing by simply the inverse of the sync. There was the sync with the null. I'm very naively equalizing with the inverse. But anyway, and this is a real recording. This is not a simulation. This is a real recording. You may see that text is they're somewhat clearer. So we see here Tempest SDR remotely, it's much clearer. This part here, you may see that before it was not possible to read it. There is a little bit clearer, but now remotely it's YouTube, the symbol. Again, here we have two problems, not one. We have the frequency error problem plus how to equalize, blind equalization. Oh, that's an open problem. Now, regarding the digital case, where equalization is clearly not possible because we're talking about bits there, so equalizing is not really a sensible path. There are some works that use deep learning to reconstruct the image or to recognize characters. We're starting to work on that. But the message here is you should not throw away one of the channels. So you should not consider for your deep learning framework the magnitude of the complex. You should consider like the whole complex to reconstruct the image. We provide a signal simulator that if you for ourselves, we're going to use it to ease the construction of the training set, but it's available there if anyone wants to address the problem in this fashion. It may prove useful. And well, that's all. Thank you very much. There you have my mail, my Twitter. This is the the GitHub of Geotempest. We also share several recordings if you want to test the system and you don't have a USRP. And I would like to thank especially Pablo Menoni, with whom I worked on his master thesis and with whom I understood Tempest. So I'm going to be around for questions. Thank you.